All right, welcome back to the second part in the series on cosmic background radiation. Hopefully you caught the first part where we went over in detail the formulation and the methods that we're going to be using in order to crack this problem, in order to get the temperature out of the spectrum data that we're going to do. So now what we're going to do is focus strictly on the Python. So in this particular video, what we're going to do is get the Python code worked out. And again, just remember that the GitHub repository, the link to that is in the description box below. And that'll be what we're focusing on. So today we'll find out if in fact this method works or not. And if it does work, what kind of answer does it give us and how does it compare to the known result that NASA has shared with us already. All right, so that's what we're going to be doing today. Thank you guys for kind of hanging around. If you watched the first video and you're still with us, we appreciate you joining us for this number 2. All right, so let's get to it. We're getting ready to work this stuff out in Python, and that's all I got to say. All right, so let's have some fun with it. All right, peace. So let's get started now using Python. Let's see if we can bring the formulation that we just went through to fruition. Now, what you're looking at now is a file that I went ahead and just constructed before, of course, the video started. But so these are just some constants that I'm going to be making use of. Some of them, not every one of them, but most of them I'm going to be using. And so I'm just go ahead and putting them in a separate file, which you see labeled here, the QMFSB_constants. So I'm just showing you this just so you know where this comes from. So just a file that has a few constants in it, and we're going to be making use of this in the main script that we're getting ready to create. And then I wanted to also show you that there is a directory in our project file named called data files, and inside of here there is a file, a CSV file, which contains the data that we're going to be fitting. And this is just 2 columns of data. The first column being the frequency, or 1/, centimeters, inverse centimeters, and then this second column being the amplitude of the actual spectrum data, all right, corresponding to whatever value of frequency. So these are the data that we're going to be fitting, which were taken from the figure that we discussed in the slides. So all right, so we're just showing you kind of, so we got this directory, data files. Inside of there is where the actual data resides. So you'll see we're going to have that referenced in the code, just so you know what we're talking about. All right, so let's go ahead and start a new file, and let's see here. All right, so we're going to start a new file, a new Python script. And so we just come over here, come down to the Python file, and let's see, let's just give it some, give it a name that, whatever makes it easier for you to remember, but we're going to give it a name. All right, and that's it. Should be good. All right, so now we have this clean slate that we're going to start with. So of course we're going to first bring in some modules that we're going to need just to get this accomplished. And as we just saw, we were looking at CSV data, and when we do that, it means that we're going to need to process this type of some data from a text file. So in order to do that, we're going to bring in a module, and then we're going to be doing, I'm sure you probably noticed in the slides, that there's quite a bit of mathematics going on. So we're going to also need some modules to help us implement some of that stuff. All right, so I'm going to basically bring in some of these modules. The infamous NumPy, we're bringing in as NP. We're going to bring in math module. Let's do that. And then we're going to bring in, and this is mostly for, or not mostly, it's only for plots that we're going to be doing, so we can visualize and see, the data that we're going to be generating. All right, so let's do that. So we got this module, and then we also have, now for processing that data that we just saw in the CSV file, we're going to bring in a module called CSV, and that allows us to read in that data the way that we want. And then we're going to bring in now the constants from that file that we I just showed you. And so we're going to bring it in. I'm going to give it a pseudo name or abbreviated name and just call it const. And you'll see how I reference variables from there. I'm going to have to use this abbreviated name, cons dot whatever the variable name is, and you'll see that in just a little bit. All right, so these are the modules that we're going to be using for this. And now I also want to kind of mention that there's quite a bit of stuff that we have to code here. This is not the shortest script, that we're going to have to create. And I want people who are following along to be able to reproduce and generate, the code. So what I'm going to be doing is I'm going to slow down on some parts, and then other parts I'm just going to fast forward, because since you're watching a video, you can just freeze it on the parts where you need to copy code. So what I'm going to do is only stop in the places where I want to kind of stop and explain some things about what I'm doing. But if you remember, we had a lot of functions that we required. Like we had Planck's function. We needed its two derivatives, the first and second derivative with respect to temperature. We also needed that function corresponding to the maximum of the Planck function. And we needed its first and second derivatives. And then we also needed the norm function, which is which combines those two. And we needed that function's first and second derivative. And so all of that was necessary so we can construct that function that's needed in Newton's method. And that method required both what we call f of temperature, f of t, as well as its derivative. So this is the reason why we had to go all the way up to second derivatives. So there's, coding all of these functions can be a little bit tedious. And this is some of the part I'm not going to go through line by line. I'm just going to kind of do it in one fell swoop, and then you can feel free to stop the video in places where you want to. I'm going to just letting you know how the flow in which this thing will go. So first I'm going to define some variables that we need. So let's first go ahead and introduce the file name that we just saw that contains the data that we're going to need. And it was in a directory, remember, if you recall, data files. And the file name is just cobe.csv. And that's the file. If you recall, we looked at that just a moment ago, and that's this file. All right. So we're just basically storing the name of that file, or the path to that file, in a variable. So, because we're going to use it in just a little bit. And then I'm going to introduce another variable, which actually comes from I'm going to be using in order to calculate this variable, or this constant, I should say. We're going to be using variables from this kind of stack of variables that we just brought in. All right. So this is basically going to be a ratio, and you'll see. So we're going to basically use, and we'll open up the file in just a second so you can see what this is. But I'm basically, if you recall, when we were looking at the maximum wavelength, we had to construct this function that involved the constant relating to what's known as Wien's displacement. And we had, and if you're watching this, you probably are unaware, but there's another lab which is done in the whole course that this is a part of, where we calculate the roots for Wien's displacement law, and we need to use that root that we calculated there in order to use it in this module. All right, so we're just going to take that root that we calculated, and then we're going to use that, and then we're also going to bring in Boltzmann's constant, and then all of this is going to be divided by Planck's constant. All right, so we're going to use this throughout in several functions that we're going to be coding. So that's why we're introducing it. And then we're going to need an initial temperature, and we'll see where this comes into the picture in just a bit. But this is something that we're going to use. We'll see it when the time is right, when we start actually doing the iterations in the Newton's method. But for now, we're going to set up some kind of little constants or variables that we're going to use to run things and control the script. All right. So we're going to have an integer count that we're going to be using as well. That's going to control basically when we do Newton's iteration. We're going to use this integer to control whether we, basically go over a certain number of designated iterations. And if we do, then we're going to kick out of the loop and things like that. All right. So that's what this is for. And this number is going to be the defined number of maximum iterations that we will use in the Newton's iteration to kick out should we not converge, and we don't want to be stuck in an infinite loop if for some reason the algorithm doesn't converge. So we want to make sure that we do. So that's what the use of iCount and iMax are going to be for. All right. Now we're also going to need something, an initial value for what is referred to as epsilon, or this error that we're going to be using also in Newton's method, and we'll see that in shortly. So we're going to get that in there, and then we also have to define a threshold. And so we want to basically have some number that will be satisfied, or satisfying this value to be less than this value, we will be, satisfies the definition of converged. And we'll see that, that in action when we run the script. But this is something that we want to make sure that we define. And these, it's typically a small number that's going to be approaching 0. And we just say, once you get below this value, we'll consider it converged. And you'll see this in action, so it'll make more sense if it's not making much sense now. And then I'm going to introduce something called beta, which for now is just going to have the value of 1. But we're going to play with it towards the end of this part. But for now, it's just going to have a certain value of 1. But you'll understand. We're also going to use it in Newton's iterative method. But for now, I won't say too much more about it. But when we get to it, it'll be easier to explain what its purpose is. All right. Okay. So now at this point, I'm going to start kind of coding out a number of the functions. There's like 12 or so functions that I have to actually code out. So I'm going to do this first one just to kind of explain what I'm doing with processing the CSV, comma separated variable file, the data from the satellite. But then after that, I'm going to probably just type out without, talking to you guys and let it, just kind of flow through that part. I'll probably change the speed as well, just so that can be a little bit quicker. And feel free to just stop it in places where you need to, look at the screen. Okay. All right. So first method that we're going to define is we're going to bring in the data. All right. So we're going to get this, the data that from the satellite, or like I said, any data. If someone has data, all we need to do is specify the path for that in this f name. And then after that, we just pass it to this function, or to this method. All right. So the first thing that we're going to do is these are going to be for the amplitude data and then for the frequency data. And so the frequency data, I'm calling it lambda. It's not actually the most accurate name, but it's actually 1 over wavelength, which is actually proportional to frequency. And then what we're going to do is we're going to basically loop through all of the rows of the CSV file and dump the things in these respective arrays or iterables or lists that we have here, in dat and lam. All right, so that's what's going to be going on. So we're going to basically with open, and then we're going to pass now wherever the path to where that CSV file is. And then this is just going to be the reference that we're going to use. And now what we're going to do is call some of the methods that are available from CSV, which is what we imported above. So we're going to say CSV and reader, and we're going to say, we now going to basically call this method called reader, and you need to pass in some things. So one is CSV file. So we're going to pass in this, and which is the object that's kind of stuff from this, from the file that we already pointed to. So we have this CSV that's reading on our CSV file, and then we need to also pass in, and there's probably a default delimiter, but in case, it's a good idea to basically specify it should you have something different. So there is a delimiter that's used that separates the data, let's say the columns in your file. So you can specify that explicitly. So in our file, it's basically just a comma, which is, and so let's go back and look at that. So this is, if you see what separates one number from another is going to be a comma. So this is the delimiter here. So that's what we're telling this method, that is the delimiter. And so that's why we're basically, just telling it what it is. So should that be anything other than a comma, then this would be the place to specify that. Okay. All right. So once we have that, we're now inside of the loop. So we can go ahead and start to loop through everything that's in this, the CSV reader object that's basically pulled from our file. So let's do that. So I'm going to count of some things. So I'm going to specify a counter, and then we're going to say basically we're going to loop a for loop here. So for row in CSV, and we're going to say reader, and then all I'm going to do is I'm going to and depending on the file, let me type it out first, and then I'll just finish the comment. But so let me do this condition if the count is strictly greater than 0, and this is something that you want to do if your data has in it a header. So if your data has a header and you don't want to include that in the data that you're going to obviously put inside of your arrays of these lists here, then this is just looking for starting after that. So this is basically just saying as long as the value is beyond 0, which is that very first row, because the indexes start at 0, then we'll start to, now we can start to append information or data to our list, and that's all we're doing. All right, so we're going to do that, and we're going to, depending on, I'm being a little bit cautious, I guess, with the formatting. So I'm basically typecasting or converting it to a float, and so that's why you see me, right here with this float, and then what we're passing in is what we're reading, and the format again is a number, comma, number. So it's basically like a list with two things in it, or two elements in it. So I'm referencing those with row sub 0 being the first column, really, is element in the first column, and then we'll do a similar thing for indat, and then we're gonna append to that all the corresponding value. So that's all we're doing here. And what are we going to do? We're going to take now the second one or the next one. So that's going to be sub 1, all right? Or element with index 1. And so that's that. And then I'm going to basically, not in the if loop, we're going to, continue the count, all right? So in Python, we can do that with just the plus, basically plus equals 1. And that basically increments the index here, which is started outside of the loop, and we're just indexing it while we're in the loop. All right. So that's pretty much it. So now what I want to return something from this. And so what do I want to return? I want to basically return the data here. And in case I want it, I'll also pass the count, which is just counting the number of data points in there. So let me do that. So let's return. And then what we're gonna do is return numpy, and I'm gonna do basically make sure that these lists are returned as numpy arrays, and we'll do that for each. I'm gonna return our lambda, and we're also gonna return our indat. So this is just x and y values from the data file. All right, so that's really it for reading in our data from our CSV. We're putting it in a method so we can, again, just use it for any file that obviously there's an assumption with the format of the data. And as long as that's satisfied, then we're good. All right. So, and then I'm also going to pass the L count. All right. So we can know how many rows there are. Should that data be useful? All right. So we're passing 3 things from this method. And all we got to do is call it and pass it the path to the file, to our data file. And then we will get returned to us basically the x-axis values, the y-axis values, and the total number of rows in the data file. And that's what we're passing back, and we're going to be using this, obviously, in this exercise. All right. So after this, I guess what we want to do now is call it, or, because this is just a method, so we're not doing anything with it yet. So we need to actually, use it. So let's do that. So I'm going to call this this is going to be the frequency data, and then the measurement data, which is the y-axis, and then we'll just call this m count. All right. So what I'm doing is I'm stuffing or assigning the variables that are going to, basically be assigned to what gets returned from our method. That's all we're doing. So we're going to call our method, and we got fname already defined, I should say, up here, and this is just the path to the data file that we've already seen. So we're going to pass that CSV file into this method, and it's just going to return to us numpy list or arrays, and then this number, which tells us information about the data and that we can make use of. All right, in this. And so now what I'm going to do is remember we're normalizing our data. So let me introduce well, we got to do a couple of things. One is, remember, the data is given to us with inverse centimeters. So I want to just write it in conventional frequency units, and then which SI or hertz or inverse seconds. We're going to basically convert that, and then we need to normalize the y-axis data. Remember that, because that's what we're basically doing, so that we're insensitive to whatever units that are decided to be used. As long as the data is a proper spectrum from a blackbody, then we're going to normalize it, and we'll be able to fit that data. All right. So that's what the next couple of steps we're going to do. So all I'm going to do here is get this data into the right format, and I'll just do that by, taking this we're going to take fmes. This is the x-axis data. It's not really, it's still not quite in the units yet, so we're going to overwrite what we have. And then this is, in fact, I think I call this a different variable. Excuse me. And then what we're going to do is we're going to multiply this or scale this by, and all this does is converts it, takes the inverse centimeters basically to inverse meters, and we're going to basically use that axis. So how do I do that? Just by basically scaling by 1 to the minus 2. We're just using, instead of inverse centimeters, we got inverse meters. All right, so that's what we got here. And that's actually an inverse wavelength is the units there. So that's that value. And let's see, we got extra parentheses there. So make sure you don't duplicate that. All right, so we got lambda v scale now to just be the units that we need. And then we got f. Now I'm going to write f mes v, which is going to be the final one that we need. Now this is going to be const c, which is the speed of light, divided by this, our vector here. All right. So this is basically allowing us to, now we're converting it to explicit to frequency units, because so we did it in kind of 2 steps, converting it first to inverse meters, and then taking that and then using this with C, speed of light, and then converting it to actual units of frequency, which is going to be hertz. All right. So that's what we got there, because we want to, just keep it SI, keep it, simple. And then what we want to do is get the maximum value of our measurement data, because that's what we're going to be normalizing that data by. All right, so we just take that value, and that is going to be stored in dmax, and we're going to be using that to normalize all of our measurement data. All right, so with that, we basically now we have our data read in. We have the important kind of parameters that we need, or variables that we need set up, so that we can basically control the way that we iterate through and what we iterate through to solve the problem. All right. So now what I'm going to do is I'm going to kind of stop talking for a little bit. I'm going to go ahead and code out. I'll leave the screen showing all of this, but I'm not going to talk while I'm doing it, because it's just going to slow me down. But all those functions that I mentioned that we need to code in, the Planck's distribution, its derivatives, the Pmax, all of those things, I'm going to go ahead and do those now, because there's quite a few of them. But like I said, I want to make sure that for those that are following along, you still can produce the code on your own as well. All right. So this is what we're going to do now. And so I'll talk to you when I basically get this part of it done. All right. So you won't hear me for a little bit while I'm just coding this out. Okay. All right. All right, so now that we've got all of those functions out of the way that we needed in order to even evaluate or set up, I should say, the Newton's method. So now we can actually start to basically construct the iterations and the iterations using Newton's method. So let's do that. We'll do that now. So we're going to just put a little note here. Right, and just kind of start that process. So we're going to first introduce, this is going to be the list or the vector that's going to store the I+1 value, or the updated values from Newton's iteration. And remember, above we define the initial value, whatever that value is, and we're just going to basically start with that array. So we're going to have TIP1V is what I'm going to call it, for TI+1 vector, and then that's just going to be starting out a vector that includes the initial condition. All right, so just some array that only has one value at the beginning, and then as it iterates, it's going to append those values to this list, and we'll get the complete iterative list at the end. And then we're going to also have an error vector. We're going to be able to take a look at that. It's very useful to do that, and to also help in understanding kind of the ability of the algorithm or the method that we're using to tackle the problem that we're looking at. So we'll discuss that a little bit too. So, and then this vector here is basically, we're gonna store it in, this is the value of f in the Newton's method. Remember, we got ti plus 1 is equal to ti minus f divided by f prime. So that f over f prime is actually just it's a unit of delta temperature. So it's just basically a number that has units of temperature. And so that delta t, so we're going to actually stuff those values as we iterate as well into this array. So that's what this is for. All right, so we got that. And now we can basically start to loop through. So what we're going to do is basically loop through while our epsilon, remember we have an epsilon value. That epsilon, while it's greater than our threshold, when we define that above, while it's greater than threshold, and the second condition is while the iterative count, the I, C, and T, is less than I max, which is the number that we set above, which was around 1,000. So by setting it up this way, we are sure to avoid an infinite loop because we will never go past. Well, okay, so the condition for continuing the loop is while epsilon is greater than threshold and we are less than the I max. So as soon as either one of these breaks, then the loop is going to stop. So we're either going to stop when we get above above I max, which means that we have gone past the desired number of iterations we want to go through. It means we probably aren't getting the result we want. So let's just go ahead and kill it. Or we're going to go less than the threshold, which is conditioned for convergence. So we're just basically making sure that we always come out of the loop, and we want to know under which condition we come out of the loop, which we'll see in just a second. So I'm going to print some things out while we're looping so we can take a look at some things. So one of them is the error, the convergence error that we're basically keeping track of. So we're going to basically, this is EPS, this is this epsilon value that we're going to keep track of. And then we're going to also look at this threshold. And this is because I want to see what it is always relative to what the current threshold is, because it doesn't mean anything if we don't have the current threshold value. All right, so we got threshold value, and then that's gonna go right here. We're gonna spit that out, and then last but not least is we're gonna get the actual, whatever the updated temperature value is, and we're gonna look at that. And that's what's gonna be every iteration is just gonna spit that out in the terminal of the console. All right, so that is what the purpose of this is for. And we have our initial values already set for these, remember, so we can print them out as early as the first line. So after this, what we want to do is basically start, I guess why don't we do the iteration? So we can say the ti plus 1 value, which is this is the ti plus 1, so the updated temperature is going to be equal to the previous value or the current value of temperature minus the ratio of the two functions. So remember I introduced beta above. Right now its value is 1, so it's not going to make a notable difference in this first case, but we're still going to have it in the equation, and we're going to look at what it does. And so now what we're going to do is just basically we're going to have our Newton function, and the Newton function takes in an argument. So it's going to take in the fmed, the list of measurement values, and then it's also going to take in basically our the measurement numbers. Remember, this is already normalized. And maybe it's not. No, it's not. Excuse my French. So we got to do that because we captured that number above, and I think we called it dmax. Yeah, dmax. So we're going to normalize the measurement data here, which is getting passed into Newton's method. And then we're going to also pass in the current value of the temperature. And these are the inputs that our method takes in. So we have this is their x values, or the x-axis values, or the frequencies. And these are the measurement values being normalized by its peak. And then we also have the current value of the temperature, and that's what gets taken in. And we also need to take the ratio of this with the similar thing, but with the function that is the derivative of the Newton's function. So we have that already programmed. So we have that method already constructed. So what we're going to do is just basically put it here. And so now what we're doing is we're basically iterating through, we're updating the temperature based on Newton, based on Newton's method, which is Ti plus 1 is equal to Ti minus, and then it's F over F prime. And that's all this is. All right, so now we have our updated value of temperature, so we can kind of do some stuff with it. So first, why don't we update the vector that's going to be keeping this information, the Ti P1V vector, and then we're just going to append those values, the value of Ti P1. All right, so this is how we're going to continue adding to that vector, so that we're keeping a list of all of those numbers, so we can do things with them, like see them and whatever we want to do with it later. And we also want to do our remember our delta T method. We'll do a similar thing, and that's basically the ratio, the F over F max. So that is this ratio here. So I'm just going to cut and paste that, and that is what we're going to append for the delta V. All right, so after that, we also have remember, we're keeping track of an epsilon or an error, something that represents the error. And in this method, this value is going to be given by, we're going to define it. And there's not just one way to do that. You can do that in many different ways. But what we're going to do is use a pretty conventional kind of process, equation or formula, I should say. So we're going to take the absolute value and we're going to take it of a ratio. So that ratio is going to basically be Ti, the latest value of the temperature minus the previous value, Ti, and then we're going to divide this by the latest value. So that's Ti P1. So this ratio is going to be our metric that we're going to use for establishing convergence. So when this number, EPS, goes less than the threshold, we will basically will be assumed to have converged at that point. So we're going to use that as our metric. And so now we can basically add our value to excuse me, to the error vector, and that is just going to be this EPS value. So we want to be able to access that information as well. And then we can update our Ti now becomes Ti plus 1, the latest value, and we do it all over again. But we're going to update our iterations as well. So I count, because we need to make sure we're keeping track of that. So I count is now going to go up by 1 as well. And that is really it, I think. I haven't forgotten anything. So this is basically the implementation of Newton's algorithm that basically goes through and updates this temperature value based on the function that we've been, basically formulating, our cost function, and the derivative of our cost function, I should say. And that function is at the numerator, and then its derivative is in the denominator, and we're just updating and then basically assigning the variables and their values to according places, and that's it. We're just keeping track of all that stuff, and that's it, guys and gals. So for Newton's method, so we have kind of basically this is what we worked out then, what we really want to have for the Newtons to get the temperature that we want. Everything from this point is just going to be to plot out or to look at, what the data looks like and do, things like that, which are, nothing to do with getting the answer. The answer will come out of this algorithm. So the first thing we're going to do is kind of print some stuff out so that we know what the condition is, under which we convert, whether we actually kicked out because we exceeded Imax or because we, basically converged, which is what we want. So I'm going to basically print something out according to that, depending on what the condition is. So if we have, as long as we're less than Imax, right? Because and we've converged, then we know that we're going to print, these will be the condition, I should say. So we have converged, and we're going to say, and we're going to actually spit out how many iterations it took us, and that's I, C, and T. So that's I count. And then we're going to say iterations. Okay, so that way we just are spitting out, we converged in this many iterations, and we know what our Imax is, so this will be less than that. Okay, and then what we'll do is we'll print out the estimated temperature, which is what we just converted to or calculated. Okay, so the estimated root slash temperature is going to be, that's going to be the latest value, either TI or TI plus 1. And the very last iteration, they're going to both, since we're assigning TI at the very last step, so we'll just call it TI. All right, so we got this, and if this condition is not met, then we know we have not converged, which means that we are basically either we're right at Imax before we got to reaching the convergence condition. So then we'll print something out that tells us, so we know that. All right, so we'll just print out some kind of message that says max iterations reached before convergence. Okay, so that's just for our own kind of convenience. So we have that, and we'll also print the temperature. I mean, whatever the latest value of TI. Okay, last temperature value, and we'll just so we can know what that is. Okay, in either case. So this just spits out something in the terminal that lets us know immediately under which conditions we converge, and that's good to know. So we have that, and so I think from this point what we want to do is just some visual. We're going to plot some stuff out. Remember, we imported matplotlib into our script, so we're going to make use of that as well. So everything from this point is just plotting some things out. So let me kind of put this together, and then we should be able to run it after that. All right. So let me put a little note here, just so we know we're starting that. So the first thing we're going to do is construct this object, or I should say objects, to plot things on. And we're gonna basically do a subplot here. So I'm gonna have 4 different figures on one plot, or 4 different axes really on one plot. So we got 2. I'm gonna do a 2 by 2 just to have all the data on one screen so we can check it out. All right, so first I want to basically plot out what's going to be on the first axis, which is 0, 0, the 0, 0 array. You can think of this as a array, a 2 by 2 array of plots, which we're going to be basically putting together. So the 0, 0 is going to be the top left, and we can access those by calling axis with the indices there, and then we'll call the different methods that we want. So we can plot, for example, and we'll plot FV and YV, which are values that we calculated, and we're just going to pass in some parameters to. So what we're going to basically plot out first is the data and the fit to this one, so we can see how they both compare to one another. So this is going to be the data points, and then after that we want a label just so we know what we're looking at, and we'll call it fit for this particular data. So this is FV and YV, and did I skip that in the code? Yeah, I probably did. So we have we want to calculate those vectors, and maybe I must have. All right, so we scroll. We're going to put that maybe above here. And I apologize, I'm looking at a bunch of stuff, so it's easy to miss some things. So what I want to do is, excuse me, we're going to calculate, basically, we're going to get the value, remember, we're trying to fit data, so we want to actually construct that data, reconstruct the spectral data using our fit, which is a certain temperature, and then evaluate it with values of Planck's function. So we want to do that. So the way we can do that is, basically I'm going to do a few things. So let me set up reconstruct. I'm going to just, okay. So first I'm going to, there's a couple of things I want to do. So one is I want to define a range of temperatures, because we're going to actually calculate that as well. We're going to calculate a range of temperatures, and we're going to do that so that we can look at the Newton's function, because that's going to be something useful to take a look at. All right, so now we got Newton. I'm going to call this Newton fun V vector. Just call this an empty array for now, and then we're going to populate it. So TV is going to be, we're just going to basically make a little evenly spaced out array using this information. Tmin, Tmax, and number of temperature. All right. Okay. Now, what we're going to do is we're going to loop through, and this is again, we're just going to reconstruct. We're going to calculate some things that we're going to see, and you'll see when we plot it out, it'll make more sense when we plot it out if it doesn't at this point. So we're going to basically plot out, we want to have available to us this Newton's function. We want to actually make an array of those values. So let me get ahead of myself. So Newton fund v, and we want to append this information. So Newton the function, we're going to call the Newton's function, and we're going to pass it our data, our frequency data, as well as our mes v data. This is the y-axis data, and then we got to remember to divide that by dmax, and that information is going to get passed along with the value of T, temperature. All right, so that is calculated because we want to take a look at that. It's always good information to have. And then what we're going to do in addition to this is we're going to introduce these YV, which is why I was blank, because I completely skipped it while I was doing this. All right, so and for this part, it's not much to it, but we're just going to FD loop through again our data, and then we're going to. So to do that, we're going to zip these two iterables, fmes v and our mes v. So this is our data. All right, so we're going to take this data, and what I'm going to do is take yv and append, and all we're doing is calling now the p norm value. Remember these are evaluated at the data at the measurement data point f, and also ti. Okay, so the ti value, that's not very clear what that number is. The ti value here should be, it's going to be the iterative value. Yeah, I got to make sure I put this in the right place. Which I didn't. So what I'm doing now, I need to actually put this after we iterate, and I think right now it's before, so that's going to be a problem. So we got to bring this below our iterative loop so that Ti is available, because the converged temperature, once we found the temperature, we want to make use of it to do the fitting. So that's the reason why this is being pulled to after. So that gives us YV, and FV is just going to be the x-axis, so the corresponding f-axis. All right, so we got that data, and I think that might be it. Now we can get back to the plotting. All right, so let's get back down here to our plots, and I'm just going to go ahead and code this out, and then you can feel free to stop it where you need to in order to look at something that's being typed out. Okay, so I'm just going to type this out without talking. All right, that is the last of what needs to be typed, and I see we have an error here, so we need to fix this. So I see there's one error, which is around here. Okay, So completely forgot to actually define the denominator for this particular function. So p prime, den denominator. Let's get that part taken care of. We have u, so minus 1, and then we square that. Okay, that's the denominator that goes there. All right, so we've cleaned up that error. Yeah, I think hopefully that is the last of the errors. Okay. All right. Okay. Whew. All right. So let's just give it a try, because hopefully this will run. I mean, I know in principle it should run, but let's see with what we have so far typed out, that we get something going. So we got our initial value set, we got imax set, we have a threshold set, we have beta set. So let's see if we can get something out of this. Let's go. Oh, should have right click. We got an error, and it says that type error is missing required positional argument. So we got to fix that. There's a temperature missing from here. Okay, so I think that must mean the Newton fund. So let's go find our Newton function. I think we forgot something there. Should be later. Here. We have temperature. Let's see, 114. Let's put it in the wrong place. Okay. It needs to be the argument of the Newton function, so not outside of it. Okay, let's see if we can get something going with that. All right, we got some more errors. And what is the problem here? It says legal value. Okay, so they're coming from a subplot, but even still, we're not getting a number that makes any sense there. Okay, so sorry about that. I had to take a second to figure out what was going on, and I'm glad I did, because I don't think you would have enjoyed looking for what I had to find. So I definitely have made some boo-boos, and I want to point these corrections out so that you don't continue them. Let's go ahead and start up. So we got to first go back up to the function p prime. There's an error there. P prime, that's the derivative of Planck's function. So if we go up here to p prime, let's make some corrections here so that things will work correctly. So first we go to this variable here, coefficient, and so this is the corrected form, and you probably have something different if you just type what I typed. But I didn't square Planck's constant, so make sure you square this. So I forgot this square, and then make sure that in the numerator here, I think I forgot Boltzmann's constant, which is kind of a big deal. So this should be k times c cubed. All right, so that's what this should be. It's const.k. It's pulling that in from that constants file of constants that we have. So make sure that your coefficient actually has this in it rather than what we typed the first time. And there's some others that we need to point out as well. And in this place, we need to add some parentheses somewhere that made the mathematical interpretation erroneous. And that is in the pmax function, and also its subsequent functions. So if we go down to pmax, this is the corrected version. If you go down to pmax, I had omitted this parentheses here. There was not a parentheses here, so it was multiplying this number by this number and then subtracting 1, which is not what it's supposed to do. So you need to surround the exponential minus 1 so that it is a term of its own. All right, so you put the parentheses here and then copy and paste this coefficient. Once you make that correction, copy and paste this everywhere in these 3 places, and the pmax and its 2 derivatives. So just make sure you propagate that correction to the other functions as well. All right, so make sure you do that. And I think that, and then there's one more in the plotting part where there was a typo. that needs to be corrected. And if you come down to the bottom where I'm doing axis 0, 1, I think some of you, the first time at least I had B0 dot. So that this means blue circles, but B0 period will kick an error out because it doesn't know that. So what I wanted was dash dot dot, which tells it to do a line, kind of a dash line with alternating dash and dot. That's what this means. So there was a typo there, so make sure you correct that. And I think hopefully with those you should be good to go. So now we can run this. So we have our initial condition set up here, and then we're just going to basically run this. It's going to do all what it does, and then we're going to actually get to see. It's going to spit out some stuff in the terminal, and we're also going to get a plot of the data that we just generated. So let's run it. Check it out. No, excuse me. We got it. All right, so we got the plot. And before we look at the plot, let's just come down here and look at what's spitting out of the terminal. You'll see we're spitting out information here. So this is the error, and we can see that the error, the first number is the error, and this starts out at 1, and then it really jumps down, and we can see that it's showing this conditions of convergence, or it's showing, the behavior that we would expect for something that's converging. So it's just basically shrinking and shrinking and shrinking in comparison to our threshold, and we can see the temperature is basically also going down to some value that we see here, and then we're spitting out here, and it just says that we did it in about 8 iterations, and this is the final temperature that we actually converge to. And if we open up our plot, we'll see a lot of the data that, so here on the left, this figure is the data, which is the red dots, and then we have the actual fit, which is the dotted line, which hopefully you can see this, which is the fitted line, which is basically pretty much right on top of our data points. And over here, we're plotting out the actual temperature, the iterated temperatures. We started out at our initial value of 3.9 or so. And then what we see here is just the actual nice smooth convergence to the actual final converged value, which is printed out up here, which is 2.723 Kelvin. All right. And so if you're familiar with the cosmic background radiation, the temperature that's known as 2.725. All right. So 2.725, and we're getting 2.723. And some of that error, in all transparency, comes, definitely from the fact that when I took these, I don't actually use their actual data points. I actually extract them from the graph, and there's probably a little bit of error introduced in that process because I don't actually have the raw data. I took it from the figure that we saw earlier, and the data is then taken from there and put into our own text file. So some of that error is probably expected to contribute to this. But still, I think that's pretty good that we get 2.723 instead of the known value of 2.725. But this is the value, and we see how the temperature converges. This is showing the error doing the same thing. It's just converging down to the threshold value, which is 1e to the minus 9. And then now here's where we want to have a conversation around, because it's very important when we talk about these types of algorithms such as the Newton's method. So this is the functional, this is the f of t that's used in Newton's method. And if you recall, we actually did some calculation where we introduced a range or a vector of temperatures, and then we went ahead and calculated what our function would be over those temperatures, over these frequencies, over these temperatures. So when we do that, we get a look at what our function looks like over temperature, close to 8. And let's see if we can get to where we want to go from there. Run this. All right, so then it did work in this instance, which, okay, so it did work. I started with 8 as the initial value, and it actually still converged to where we wanted it to go. So that I do want you to know that it's a good idea to plot out your function, the f that's used in Newton's method, and get a little bit familiar with what it looks like, how many humps there are, and if you're going to need to kind of zero in on certain regions, or sometimes you need to iterate through these different regions and do things based on where you are. So you just want to be aware of the kind of conditions that your function has, so that you get the result that you're after. Okay, and we can see though in the end that we get what we're looking for. We still get our 2.723. That's close enough to 2.725, and we can see our fit as well as our data, and everything looks pretty good. All right, so that's it. We have basically confirmed or verified the NASA values based on their data that was collected from their satellite. We started by taking their data from basically a graphic, and we fit that data, basically defining our own cost function and minimizing, all of that stuff, and then, putting that all in Python to see what we can get out of there, and we were able to do it. All right. So I hope that was helpful. And please make sure you check out, basically if I went a little fast, just pause it where you need to, and hopefully you'll be able to, get the same result. You should, because I didn't leave anything out. So, and make sure you pay attention to those corrections that I pointed out towards the end. Okay. All right, guys. Thanks for watching, and I'll see you on the next time. Thanks. Bye-bye.